start by taking attendance and continue chapter 2. We talked about fatigue last week. Have a few slides with some pictures and a graph. When you design something, you want to obviously take that into account as well as wear and corrosion. Fatigue results in repeating cycles, and if you have a positive and negative sigma, for example, which is much less than ultimate stress, if you still have a large number of cycles, failure can occur. And we have some numbers here which are sort of interesting. For example, beam supporting an industrial crane may be loaded as many as 2 million times in 25 years. Automobile crankshaft will be loaded about 500 million times if you drive it for 200,000 miles. The same thing happens in power plants and turbines. Several hundred billion times during lifetime. And this is called the sigma n curve. This is the stress. Obviously, that's the amplitude because the stress varies. And KSI means PSI, and this is a number of completely reverse cycles before failure occurs. For example, for this aluminum 2024 alloy, if your stress goes between plus and minus 30,000 psi, which is here, and the number of cycles before failure is about 500,000. The higher the stress, the lower the number of cycles before you can have failure. Same thing is shown here, and here are some pictures. This is an Aloha Airlines Boeing 737. I don't remember the exact year, but this is something like 30 years ago. But clearly there's a big piece of the fuselage which has been detached because of fatigue. And unfortunately, one person died because when something like this happens, we have pressurized cabin and very low pressure outside. So if you're not wearing your seatbelt, you can easily sucked out of the plane, and this happened to one person. Here's another picture, Southwest Airlines with significant damage here as a result of fatigue. And here is a brand new subject, the thermal stresses. We have a piece of material shown in blue here, and it is just sitting on a table. And you have an initial length of L, and then raise the temperature of this material by delta T. That's delta uppercase T. Then this material would freely stretch by a very small amount, which is this delta T. This means deformation due to temperature change. Highly exaggerated as usual, so we can see better what's happening. And the elongation due to temperature change is shown by this simple equation in which alpha is coefficient of thermal expansion, comes out of our tables. L is the initial length, and this is temperature change. Do you think there will be stresses developed in the material as a result of what we're doing here? Yes? Stress requires force, right? Force over area. Do you see any forces here? I don't. As long as you allow the material to freely stretch, there are no forces pushing on it or pulling on it, so there is no stress induced. But if you prevent the free elongation or inhibit that, then there will be stresses. Prevent and inhibit don't mean the same thing. Prevent means we don't allow any elongation, and inhibit means we allow some elongation, but not as much as what the material wants to do. But before we talk more about that, let's make sure we understand our symbols. One last time. This delta T is deformation due to temperature change. Alpha is from a table. Coefficient of thermal expansion. L is the original length shown here. And this is temperature change. Here are tables from your book. I have highlighted the column corresponding to alpha in yellow here and here. SI units on the left, English units on the right. As you can see, in this equation, delta T would have units of inches. Same with L, so those cancel. That means alpha delta temperature must be dimensionless or unitless. A delta T is Celsius or Fahrenheit. That means alpha is per degree Celsius or per degrees Fahrenheit, as you can see here. As an example, we look at the steel in the first row. Alpha is 11.7 times 10 to the minus 6 per degree C, or 6.5 times 10 to the minus 6 per degrees Fahrenheit. And this is a table we've seen before from a different table. This column with the arrow shows alpha. The numbers outside the parentheses are per degrees Fahrenheit, and inside parentheses per degrees Celsius. So, if we put this material between two rigid supports, that means we cannot have any elongation. And if you still raise the temperature, then two things happen simultaneously. If you increase the temperature, the material wants to get longer, meaning it will be pushing against both supports. The supports will push back, and we are going to have a compressive normal stress signal given by this lower equation here. PL over AE, does that look familiar? We used it multiple times last week. Elongation due to a force. And the first equation is what we just looked at, elongation due to temperature change. As you can see, both equations are linear. That means if you double the force from the wall, that will double the elongation. And in the first equation, if you double the temperature change, that also doubles the elongation. So these are linear equations, meaning we can use the method of superposition. Look at the effect of temperature change and the force from the wall separately, add the solutions. What this means is that we are imagining that the right wall has been removed, as you can see in this figure, and this is the effect of temperature change. The material simply elongates by this amount, given by the first equation. Eliminating the wall means that we have removed the force, P. And then we have to put it back, as shown here, and that will cause a deformation according to this equation. The net elongation will be the summation of those two pieces. So we are going to have a total elongation, which is the summation of PL over A, piece 1, or piece 2, plus L alpha delta T. So superposition, effect of the force, effect of temperature rise separately, and then we add the two pieces. So what is the total elongation equal to in a case like this, where the walls are fixed and rigid? Do you say 0? Because this material cannot elongate, right? It's between two rigid supports. So we set this equal to 0. And going to just erase this part here. We divide by L, and both of them disappear, so this goes away, and this. And we identify E over A as sigma, right? Or solar area. So this is sigma. So what I have is sigma divided by E is equal to minus alpha delta T, or sigma is minus D alpha delta T. So this is the stress induced in the material because of the temperature rise, and that has been highlighted in yellow on the slide. If you raise the temperature, delta T is positive, but the minus sign in the equation tells us that we have compressive normal stress, and vice versa. To reduce the temperature, the material wants to get shorter. We'll be pulling on the walls pull back, and we will have positive sigma corresponding to tension. Questions about this situation here? And here's a numerical example in which we have an initial tensile stress of 16,000 psi in a 1-inch diameter steel rod, fastened securely between two rigid walls. The temperature is increased by 50 degrees Fahrenheit. We want to find the final stress. If you have an initial stress, we simply add it to the right side of that equation. Sigma O means original or initial stress. And tension is positive, so sigma O is plus 16,000 psi. This is a piece of that table from the other book, not your textbook, showing you E of steel, 29 million psi, and 6.5 times 10 to the minus 6 per degrees Fahrenheit. So this is E. This is for the million psi, 10 to the 6. This is alpha, and this is the temperature in degrees Fahrenheit. The units automatically work out, and you get the final result in PSI. If you want to, you can write them out and cross out the units, but if you stay with standard units everywhere, inches, not feet, PSI for everything, E, etc., then you get the result in automatic, standard units for sigma, which is PSI. Any questions about this example? No? As a result of this, if you look at railroad tracks, they have gaps in them, so the material can elongate during the summer and shrink in size during winter. Like today, the temperature was 2 when I was driving to work, but it has really warmed up right now to 8 degrees. If you look at sidewalks, you can see that there are usually square blocks which have gaps in it, right? You don't have one big concrete piece, so the gaps allow the material to freely move. You might have noticed that when you're driving under a bridge, if you look up, the overpass does have a gap in it, right? That's because these beams get longer in the summer and get shorter in winter. So we don't want additional stresses as a result of temperature changes. This is a question which asks, it says that brass could not be used to reinforce concrete. Concrete is very strong in compression but quite weak in tension and easily cracks. That's why it's usually reinforced with steel rods. So the steel takes care of tension, and the compression, most of it is handled by the concrete. But we cannot do the same thing with brass instead of steel. The reason is that their alphas are very different. Alpha coefficient thermal expansion for concrete shown here. This is concrete. Alpha is 6 times 10 to the minus 6 per degrees Fahrenheit. This phi here is really should be an F. No, phi is Greek version of the letter F. So this is obviously a font problem. So this is per degrees Fahrenheit. 6 for concrete. If you look at steel, it is in this table 6.5. We just use this number in our example, 6.5 times 10 to the minus 6. Or if we go back to these tables, this is 6.5 times 10 to the minus 6. Table from your book, same thing, 6.5 times 10 to the minus 6. So as you can see, they're close. 6.5 for steel, 6 for concrete. But if you look at brass, red brass, which is here, alpha is 9.8 times 10 to the minus 6 per degrees Fahrenheit. 6 and 9.8 are quite different numbers, but 6 and 6.5 are very close. So what do you think will happen if the alphas are very different? Brass versus concrete. If you reinforce concrete with brass and the temperature changes, because the alphas are very different, the materials stretch by different amounts. So they are going to separate. Questions about this example? The next topic is the Poisson ratio. Anybody here speaks French? No. Poisson in French means fish. So clearly this is the name of a person that came up with this phenomenon, Mr. Fish. And it really is a very simple idea. It means that if you apply an axial force to a rod, like let's draw it in 3D. And axial means in the horizontal direction here, x. Y would be usually going up, and Z will come out of the board. So axial means along the length of the material. If we apply a force P here, and the same force here in the opposite direction. Both of these forces result in tension. Agree? Positive sigma. And so which force would you say is the positive? The one on the right or the one on the left? The one on the right? Well, in this subject, in this class, because the forces are both doing the same thing, causing tension, this combination is positive, results in tension, positive sigma. If you reverse both, they both become negative. So if you're doing this, then we're going to obviously have a sigma in the x direction. And that's E times epsilon in the x direction. What's the name of this law?
Hooke's law.
Hooke's law, right? We saw it last week.
Bless you.
And what's the name of E? Modulus of elasticity is one of the columns in table. So, in this case, epsilon x will be a small positive number because the material gets longer in the x direction. But at the same time, the cross-section shrinks in size. So we will have a negative epsilon y, which is the same as epsilon z, and they are minus nu times epsilon x, where nu is called the Poisson ratio. What it says simply is that if this material elongates horizontally, the cross-section shrinks in both y and z directions, so the epsilon will be negative, that's why we have a minus sign here, and nu is a number which does not have any units, and it's 0.30 for steel. This is the column for Poisson ratio, nu, 0.30 for steel. What this means is that if you apply force horizontally, and this rod gets longer by 1%, the cross-section gets smaller by 0.3%. That's all this means. And X direction is called axial. Direction. Y and Z are in the cross section and they're called lateral directions. So when you look at this slide here, Poisson ratio is minus lateral strain in the cross section divided by axial or longitudinal strain. And again, this is 0.30 for steel, which is the material we use in most of our examples. This is Hooke's law. So you could solve this for epsilon and plug it into here, so that becomes minus nu sigma x divided by here in this figure, we have a cylindrical rod, so it is a diameter d shown here. And here we are applying the forces vertically, so axial is vertical direction, lateral means in the cross section. The L gets bigger, the diameter shrinks in size, so we go from here to here. Smaller diameter, longer rod. Questions about the Poisson ratio? Your book does not have a column for Poisson ratio. So if you look at this table, there is no Poisson ratio. The reason is that based on the information that we do have in these tables, we can easily calculate Poisson ratios. That's why it's not shown. And here's the example I want you to work on. Taking about 5 minutes or so. And it says that we have a cylindrical rod like this. And we are applying an axial force of 150,000 pounds. Vertically, causing tension in this material. And this is our x direction. So here axial is vertical, and the diameter, initial diameter is 2 inches. So that is this. And the material is steel, so Poisson ratio is 0.30. We just saw this in our table. And we're asked to find the new diameter. And you have the answer. We go from 2 inches to 1.999. Clearly a very small reduction in diameter. And you have all the equations that you need right here on the board. So instead of Y and Z, we want to use D for what happens to diameter. Nu is 0.3, sigma is force over area, E is modulus of elasticity, which is how many psi for steel? We've done quite a few problems involving steel, so this is 29 million. But there's no reason really to memorize these numbers because you can always use tables. 29 million psi.
Yeah.
So this becomes epsilon in the diameter direction is minus nu. Yeah, sigma is P over A. And epsilon D means the change in diameter divided by the initial diameter. So let's spend 4 or 5 minutes to crunch the numbers, and hopefully you will agree with the answer highlighted here. So we want to find the change in diameter. So all you need to do is take this, multiply the left side by D. And area is pi r squared. R is half of diameter, so it's 1 inch. And plug in the number. So we will have delta D is equal to minus nu ED divided by 80. And we use standard units, so P will be 150,000 pounds. This is 0.3, no units for Poisson ratio. 2 inches, pi r squared, and R is 1 inch. And D is 29 million. And here are the numbers. This is this equation here. 0.3 for nu, 2 inches for D, force 150,000. Area is pi r squared, and R is 1. So area is just pi. And E is 29 million. And we do have a minus here, so the diameter goes down by 0.001. So it goes from 2 to 1.999 inches. questions about this problem? No? As we are doing this, the material gets longer, but the cross section shrinks. And this equation gives you the change in volume. Obviously, we are skipping some derivations here. So here V means volume, delta V means change in volume. On the right side, we have epsilon x, which is this, according to Hooke's law, and nu is the Poisson ratio. So clearly, if nu is less than 0.5, what's in parentheses will be positive, and the volume goes up. If nu is exactly 0.5, then what's in parentheses will become 0. There will be no change in volume. And if nu is bigger than 0.5, then the volume goes down. If you look at our table showing values for Poisson ratio, this column here, none of these numbers are bigger than 0.5. So for all these materials listed here, if you do something like this, the volume goes up. Not by much, but very small amount. It is not impossible to have a material with nu of bigger than 0.5, but it's very unlikely that you pull on a material and the volume actually goes down. And we're going to do this page in one example and take our usual break. So we are back to this situation in which all we are doing is apply a pair of forces in the x direction, which is called axial direction. This is Hooke's law. Sigma x is E times epsilon x. Clearly for this case, epsilon x will be positive because the material will get longer in the x direction, but the cross section will shrink in size according to this equation, which is really definition of Poisson ratio. Any thoughts of it? So this is Hooke's law in the axial direction. The question is, does this law also work in the cross section? In other words, is sigma y equal to E times epsilon y? And similarly, the same thing in the z direction. What's your answer? Epsilon x is a positive number. These will be negative, right? Because of the minus sign. So let's do that. So epsilon y and epsilon z are negative numbers. Right side of these equations are negative numbers. What are the left sides? Sigma y and sigma z. Do you see any forces in the y and z direction? No. So sigma y and sigma z are zero. No force, no stress. So left side is zero, right side is a negative number. Obviously, Hooke's law does not work in the cross section, y and z directions. That means that Hooke's law in this form is very dangerous because sometimes it works, sometimes it doesn't. That's why we need what's on this slide, generalized Hooke's laws. These equations always work in every problem. You could have forces in one direction, two directions, or all three, and those Hooke's law, that the ones shown on the left side of this slide always work, so we want to make sure that we don't use this simple equation in the cross section in a one-dimensional situation like that. So if I take the first equation, which is this, epsilon x is 1 divided by e times sigma x minus nu times sigma y plus sigma z. And apply it to this situation. What number should I use for sigma y and sigma z over here? Zeros, no force, no stress in the y and z direction. So if I cross out this and this, then this becomes epsilon x is 1 divided by e times sigma x, which is a simple Hooke's law. That we have here. So obviously that equation does work in the x direction. So what if I use the second equation listed there, which is epsilon y is 1 over e times sigma y minus nu times sigma x plus sigma z. Still, we have no stresses in the y direction or z direction because we don't have any forces. So I can cross those out, meaning this becomes epsilon y equals 1 over e times minus nu sigma x. Then I could write this as minus nu times sigma x divided by e. Sigma x divided by e is epsilon x. Is this a correct equation? This is equal to that. Yes, it is. So all of those equations work in one-dimensional problems, two-dimensional, or three-dimensional. The one at the right side of this page you can ignore for now, but we'll talk about these after the break. But want to do one example before we take a break, and that's this. We have a cube and it's 50 millimeters on the side. Material is steel. So we could look up Poisson ratio, which will be 0.30 for steel. So this is what it looks like. It's a cube. 50 millimeters on the side. And we use nu of 0.30 from our table. And we place this cube inside of an enclosure which has a pressurized gas in it, and the pressure is 200 megapascal. This is a very high pressure because atmospheric pressure is about 100 kilopascal. So 200 megapascal is a lot bigger. As a result, this cube is going to shrink in size a little bit, and we want to find the reduction in one dimension, which is initially 50. And this cube doesn't look like a cube, but let's pretend that it is. Pressure is force divided by area, and so is normal stress, right? Both are force divided by area. The only difference is that pressure forces always push on the surface. So positive pressure means compression. In solids, we use positive sigma for tension. So what this means is that our sigma, which is clearly the same in all directions for this problem, is minus 200 megapascal because it's compressive. And we got our Hooke's law on the slide that we don't see anymore, but we have that, one of those equations here. And you don't have to do this 3 times because whatever happens in the x direction also happens in the y and z direction. So all we need to do is just do this 1 time. Meaning epsilon x is 1 divided by 200 times 10 to the 9th. E of steel is 200 gigapascal from our tables. This is the same as 29 million PSI. And maybe we should just take a quick look at it again. Here is 200 gigapascal, table from your book. The same thing. 200 gigapascal. So that's the source of those numbers. All sigmas are the same, and they're all negative 200 megapascal. So instead of doing that conversion 3 times, these are no longer crossed out. So I use minus 200 for sigma x minus 0.30, and sigma y and sigma z are also minus 200. But the mega, I will do this once for all of them. So this 10 to the 9th is for giga. This is for mega, which applies to all 3 sigmas. Nu does not have any unit. So epsilon x means change in dimension divided by the original length. And L was 50 millimeters. And here are the numbers. Values of A and nu for steel, sigmas are all the same. They are negative because of compression. And that's the equation that I have right here on the right side. And the numbers, this million here cancels 6 of these. So I can erase this and change this to 3. That's what I've done over here. And this is epsilon, which is a very small negative number. If you multiply it by the initial length of 50 millimeters, you get the change in 1 dimension of the cube in millimeters, and the answer is 0.02. Questions about this problem? Nope. So we will take a 10-minute break and continue with the rest of chapter 2. Well, this is the last section to be covered today, followed by a couple of examples. We talked about shear stress last week, and you saw similar figures to these plates connected through a rivet. Those are shown down here in yellow. Or we could be using bolts. So if you look at this situation and make a cut right in the middle of the rivet here and look at what's above it, we're going to have a figure like this. This is the upper plate, and this is top half of the rivet, and we've made a cut here, right through the rivet. And we have a force P applied to the upper plate to the left. That means we must have the same force here coming from the bottom half of that rivet. As you can see, that force is parallel to the cut we have made. Therefore, it's a shear force. And we use the symbol V for that. So that will be numerically equal to this force. And that shear stress tau is defined as V divided by A, where A is the cross-sectional area of the rivet. You see that equation in blue, and the units are clearly the same as sigma, PSI, megapascal, etc. And we had Hooke's law, which looks like this. Sigma is E times epsilon. Where E is modulus of elasticity. Now we have a similar equation, tau is G times gamma, and this is called Hooke's law for shear. G is called modulus of rigidity. And gamma is called shear strain. It must be in radians, not in degrees. And as you can see in that figure, if we have a block which is rigidly attached to a surface on the bottom side, welded or glued so the bottom surface cannot move, and we apply a shear force here at the top surface, then the bottom surface cannot move, but the top surface will. And then our block is going to look like this. And this is the angle gamma, same one over here. And A is the area as seen from the top. So this is shear strain. And shear stress is tau, shear strain is an angle gamma expressed in radians. Do you think radians are real units? Or can we just throw them out at will, or bring them in as needed? So look at this simple equation giving you the perimeter of a circle. I D, where D is diameter. So perimeter would be in units such as inches. Diameter also in inches, and pi is radians. So if you cancel the inches, you find that a radian is just there by itself. So it is not a real unit. It's a reminder that we are not doing degrees. So radians can always be thrown out as a unit, or they can be brought in as needed. So gamma is unitless, just like epsilon was. So it's never in degrees, always radians. Modulus of rigidity is the last material property that you have to deal with. It's another column in the same tables you've seen before. I have highlighted those here. These are again tables from your book, modulus of rigidity G in gigapascal. This is in PSI. If you use this table from a different book, then modulus of rigidity is shown here. Millions of PSI or billions of Pascal. So there's the column for G. And this equation with an arrow next to it relates three properties to each other. E, modulus of elasticity, G, modulus of rigidity, and nu, Poisson ratio. If any two are known, use that equation to solve for the third one. This is why your book does not have a column for Poisson ratio, because you can always calculate it using numbers for E and G. Any questions about this material? Okay, we have a couple of examples. This is the first one. We have that material shown in blue, and all the dimensions are shown on this figure. Horizontally 8 inches, vertically 6 inches, and the thickness into the screen is ½ an inch. The bottom surface is attached rigidly to a support so it cannot move. And we apply a force of 5,000 pounds, shown in green, to the top surface. As a result, the edge AB, which is this edge, moves to the right by a very small amount, 0.0012 inches. And based on this information, we are asked to find G for this material. This is the front view. The bottom surface cannot move. The top surface has moved to the right by this small amount. And this is the angle gamma, which must be in radians. As always, this movement delta is greatly exaggerated. Obviously, this figure is not to scale. This is a tiny number compared to 6 inches. So if you want to find the modulus of elasticity, which is this, we need the shear stress, tau, and the angle gamma. Tau is simply shear force divided by area. That means we take the force of 5,000 psi divided by the area at the top, which is 8 by 0.5. And we get the shear stress shown here. 5,000 pounds for the force, and the area is for this surface, which is 8 by 1/2. So a shear stress is 1,250 psi. As for gamma, we look at this triangle here, and tangent of gamma is 0.0012 divided by 6. So it'll be 0.0002 radians. Do you think I should use a tangent here or just leave it out? Clearly, I have left it out because when numbers are very small, angles in radian, tangent, sine, and the angle itself are all the same number. You can try it on your calculator, make sure it's in radian mode, type in a very small number, hit the tangent, and the number does not change. By the way, one of the biggest mistakes in exams is using degrees instead of radian. You want to make sure your calculator is in radian mode. So I have left out the tangent. If you include it, you still get the same answer shown in purple. And then the last line here is this equation solved for G. And we get the 6,250,000 PSI. So sigma, tau, E, G, they all have the same units. Megapascal or PSI, Poisson ratio nu does not have any units. Questions about this problem? No. Well, there's one more problem, and after we solve this together, we'll be done for today. So we have a similar situation, except that there are two blocks of rubber shown in gray, and in between there is a plate shown in light blue, which is rigidly connected to the blocks of rubber. And we are applying a force of 7,000 pounds to that blue plate as shown right here. And here are the dimensions, 9 inches this way. This is 1.75 inches. And into the page or screen, the width of the blocks is 3 inches. And when we do this, the edge A, which is here, moves to the left by this amount, 0.125. So let's spend a few minutes to find G of the rubber. Look at the lower block. This part doesn't move. This edge here moves to the left, like that. And this is the angle gamma, same on this side. Now we use the same technique as before, just to solve for G. And we want it in PSI. Are some of the numbers hard to see? The green ones? Yeah, that just says that the width of this figure into the screen is 3 inches. And horizontally 9 inches, and the height of each block is 1.75 inches. So this dimension is 125. This one 1.75. And into the board 3 inches. What's the shear force in each block? Is it 7,000 pounds? How much is it?
3,500.
3,500. So if you look at the blue plate, it's being pushed to the left here, 7,000 pounds. So it receives a force of 3,500 pounds from each block. So that means the shear force in each rubber block is half of the force P, which is 3,500 pounds. So that's V. And shear stress is V over A. What area would you use?
The 9 inches and the 3 inches.
9 by 3, right? Area of top of the lower block. And this will be the PSI. I have the numbers on the next slide. And gamma, or tangent of gamma, because this time the angle is not as small as it was in the previous problem. So if you use tangent, it always works. So that would be 0.125 divided by 1.75. And this will be the gradients, and G is tau divided by gamma. And here are the numbers. $129.6 for shear stress. And once you solve for gamma, the numbers are extremely close. If you use tangent of gamma, which we are, you get 0.0714, but if you do inverse tangent of that, you get 0.0713. So if you leave out the tangent here, still the numbers are very close. And I have used the second one, using the extension. So that would be 0.0713 radians. And if you divide the two numbers, this by that, you get the answer given 1818 PSI. Much lower than the number we had in the previous problem, which was in the millions. Obviously, rubber is not as rigid as steel. Questions about this problem? We are very close to the end of chapter 2, so I can easily finish that on Friday. Please do look at the sample exam on Blackboard week 2, and we'll go over those problems, and my part will be finished on Friday. Have a great day, stay warm, and I'll see you Friday morning.